To tell or not tell? Okay, great. Well, I want to first thank Dave and John for the invitation to come out, tell you a little bit about our Energy Frontier Research Center. I typically go on the road now and give more overview talks, and so I thought today, given I was coming to one of the meccas of material science, it made more sense to tell you about some of the specific material science we're doing. So I'll tell you what we're doing mostly in our Center for Inverse Design. And I will first start by saying that, is that coming through enough? Is there a light issue here at all? Or? It's up to you guys. I don't know what. And I just wanted to tell you that the work I'm going to tell you today is by a lot of people, mostly not me. Alex Zunger was really one of the visionaries with Dave Ginley on creating this EFRC center. It started before I arrived at NREL. When Alex moved on to the University of Colorado, I took over its leadership and have been managing and leading it since. We have people from Oregon State and SLAC, the Stanford Linear Accelerator, as well as Northwestern and CU Boulder. And I want to show you today that by tightly coupling theory and experiment, we can actually start to really discover some new materials. And I just want to start a little bit. If you guys think about energy in general, we're going to need at least as much energy as we use today as a planet again in 2050 or so. And that energy is probably going to have to be carbon neutral if we don't want to deal with some very serious consequences. And so a lot of people have discussed about what are some of its attributes. And at NREL, we spend a lot of time on reliability, cost, and performance, as well as what integration at scale means. And so this sustainable development of where is our next set of energy going to come from is really important. And I just want you to imagine for a moment that it's about 1893 instead of 2014, and we're talking about the world's transportation system in 1893. And it's the horse. And so this is a set of horses in New York City. Cars were almost outlawed in the very beginning, and they needed a flag in front of them to walk along. I think there's one car in here somewhere. But imagine about the emissions of a horse-based transportation system. And imagine we got together to talk about energy and transportation in the late 1800s. We'd be talking about really this dire situation, and we would do a linear extrapolation that says by 1950, every street in New York City is going to be 9 feet deep in manure. And so we've had to deal with emissions from our energy systems for a long time. And fortunately, we started using fossil energy and shift happens. And really, I think we're at another point where we need to think about what that shift is. And today's a perfect day with the weather to think about the sun as one of those sources of energy. And of course, we need to not only capture sun, but we need to convert it to energy. And I'm going to talk today about photovoltaic materials and materials by design for photovoltaic concepts. But I want to remind you that we can also take sunlight to fuels, and plants do that very well, and people are trying to do that in an artificial way, and storage is important. And also we can take that to heat. And whether we use thermoelectrics to convert then heat to electricity, or whether we use conventional steam engines, there's all sorts of ways to think about converting solar energy. New materials are important, processes are important, all the way to devices and systems. And I won't spend any time today here, except I do want to tell you that at the National Renewable Energy Lab and in my directorate, we have a very broad program looking at solar energy conversion. So very applied concepts looking at cost, efficiency, performance, and reliability, more and more so addressing manufacturing, a lot of work thinking about what next generation concepts might be. And today I'm going to talk to you about some of our fundamental research, and that is how we can discover new materials. And one of the key areas that we do at NREL that I'm not going to talk about today, but if we think about kind of current technology platforms, there's two main drivers here to reduce cost. One is to take the efficiencies of what you would do in the laboratory at a centimeter squared and make them much more efficient. But you'll see one of the bigger challenges is what you get in the laboratory versus what you get in a production facility. And closing that gap is as important, or maybe more important, than increasing the efficiency of these systems. And we spent a lot of time moving these stars to the right. And I think we're finding ourselves having to spend a lot more time now on the processing science and back to some of the fundamental material science of the deposition of these systems to close that gap between manufacturing modules and commercial modules and what you could do in the best of all cases. But today I'm going to talk about materials for solar conversion, and we'll talk about solar absorber materials, the absorbers, and we'll talk about transparent conductors. And of course these are all both very important. We need to understand, and we're talking about inorganic semiconductor materials today. And in addition to absorbers and transparent conductors, I think anyone in the audience here that's ever made a device knows there's a whole bunch of other layers as well. So we'll always be looking out for contact layers and buffer layers and other things as well. But one of the things that you find remarkable is that if we think about high-tech semiconductor materials, we really haven't explored a lot of the space commercially. There's a lot of work on silicon, germanium, gallium arsenide, and we've been able to do band gap engineering and make different band gaps. But if you're a chemist or if you think in a general material space, we haven't explored as many materials as we probably should. And one of our goals is to figure out how to do that much more efficiently. And in fact, if you go to like the solar energy utilization basic research needs from DOE, you'll find the range of materials currently available is highly limited compared to all those that could in principle be synthesized. And in fact, if you look at some of our new materials like copper, indium, selenide, or sulfides, which have actually been around for now several decades, some of those might be coined much more accidental discoveries than really designed. And we actually need to think about a much more broader base of materials. And that's exactly the focus of our Center for Inverse Design, our Energy Frontier Research Center. And it's really to understand how do we define the kinds of properties that we're looking for, and then how do we explore material sets to get those properties into the right structures. And so we're looking at defining functionalities and then really coupling theory and experiment together. It's not about just writing the Hamiltonian for a solar cell here, but really coupling theory and experiment together to find the material that has that right functionality. And so we do a lot of work on high throughput theory, and a lot of this started with inverse band structure that Alex and some of our colleagues at NREL had worked on. But we've brought into this center a lot of high throughput synthesis. Dave Ginley, who has developed this with his colleagues extensively. Also detailed characterization. We have some very specific tools that Mike Toney at Stanford Linear Accelerator has been developing for us to look at very important structural things. I'll give you some examples there. And then a lot of targeted synthesis and specialized theory. And iteratively going after this and allowing theorists and experimentalists to teach each other so that we can discover materials faster. And today I want to just show you kind of 3 short stories on what we're doing in materials discovery. And I just want to talk to you about the general process first. It really is kind of a 3-step process where we actually start to define the overarching design principles. What are you looking for functionality-wise? What do you want something to do? And then we do, after picking an initial selection of materials, and this could be tens of materials up to maybe thousands or even millions of materials, how do we rapidly screen those materials against some of those target functionalities? How do we combine that theory with some high throughput synthesis to understand what's going on? And how do we down select that to best of class materials where we can then really burrow in and understand from a synthetic standpoint, a theory standpoint, an experimental standpoint, what might be some of those new materials. And so I want to just tell you that to do this, we certainly use things like density functional theory that Walter Cohn and others have developed. But we have to develop a tool set that is an experimental tool set, a computational tool set, and a data management tool set to allow us to do this. So an important component of our center has been to take well-known theories but really do some of the corrections, some of the important modifications, and we can, and I'll show you some examples where we work a lot on thermodynamic stability, understanding band structure. We spend a lot of time using supercell calculations, how to calculate defects and understand doping, and then also use a lot of the methods that we have available at NREL and other places. And we've combined this with a set of combinatorial tools. We use a lot of RF sputtering, quite a bit of work on not only the synthesis of thin films, but also how to map these with respect to composition, structure, optical properties, surface properties, or even microscopy, and then how to actually manage that large amount of data. And so the idea is, how do we go fast, but we actually want to go very smart as we go fast. And we have two main approaches. The first one is to look at known materials where the functionality is not known and explore the functionality of known materials. There's about 160,000 materials in the inorganic crystal structure database. How do we start to explore those against the functionalities for transparent conducting oxides or PV absorbers? And the second one is to say, well, that's a great data set to start with, but there's got to be systems out there that aren't yet known. How do we explore those configurations? How do we find out which materials should exist? And how do we understand what their properties are before we go crazy trying to make them? And so we basically look at design by design principles and look at missing materials, and that's the two general approaches. I'll show you two examples here on known materials, and then I'll show you one example on where we're starting to really explore missing materials in a pretty significant way. So let me first start about looking at the inverse design of solar absorbers. And so there's a lot of design principles. There's a whole list of properties that you need for a solar absorber. But if we want to think about thin film inorganic semiconductors, absorption is going to be a very important one. And so we need to make sure we can understand the densities of states at the valence level and at the conduction level, and how we can then screen a large set of materials. And I'll show you an example where we've done that screening, and then we've actually dug in and looked at some of the absorption experimentally and theoretically for some newer materials. And so this is the inorganic, crystal structure database. How do we start to explore this database for PV properties? Or if I were to reframe that problem, how do we actually go across the periodic table, pick a certain set of materials? Let's start with the chalcopyrites, of which copper indium selenide is one. Pick valence 1 materials, pick valence 3 materials, and pick valence 6 materials, and then screen them against some metric. And the metric that we actually want to screen against is a selection criteria that Lipping Yu and Alex Unger have developed within our center. And it goes beyond the simple Shockley-Queisser assessment, which just says take a band gap and then assume a lot of things are constant and you can get a maximum efficiency. It actually looks much more at the physics of absorption, emission, and recombination. It looks at the photon energy absorption dependent absorption. And it also looks at this non-radiative combination for a lot of cases, not just where you have a direct allowed transition, but maybe you have an indirect allowed transition or a direct unallowed transition below that direct one, and the recombination rates can be very different. So we look at not just the band gaps, but we also look at the optical type and some of the non-radiative recombination losses. We can calculate all these properties. And so we basically use a very nice method that we've shown works very well for band gaps for these types of materials. You see the experimental band gap down below and the calculated band gap. And then we can actually go across the ICSD structure base for these 1, 3, 6 materials. Don't allow stoichiometry to be constrained. Output band gap type absorption spectra and electronic structure and get this SLME, spectroscopically limited maximum efficiency. And so we do that for this part of the periodic table, and you see here a number of calculations, about 300 materials that we've calculated. The SLME is a function of the calculated band gap. And in this, really quickly, you see materials like copper indium selenide and copper, not sure what that one is, and then copper gallium selenide and copper indium sulfide. But you also see a whole lot of other materials in here, things like copper indium tellurides and silver gallium tellurides. So these are other absorbers that people haven't really studied the same amount as CIS, but have been experimentally confirmed as PV type materials. And then you see other materials that actually have not yet been looked at, and those might make a lot of sense to look at. And some of those are systems with thallium that you may not want to look at. But we actually have looked at some of these systems, and if I just want to take a look for a moment, what you see in this system is, if you think about these 1, 3, 6 systems, the 3 element actually can be in a valence 1 or a valence 3. And in fact, if you look at the calculated absorption spectra, we actually find that the valence 1 absorption spectrum has stronger absorption than the valence 3 absorption spectrum. And in fact, what we think of is that there's a lot more P in the conduction band and a lot more S in the valence band that gives you a higher overlap of density of states for that absorptivity. So we wanted to probe that more experimentally and theoretically, not just theoretically. And so to do that, we actually went to another system, which was to say, let's look at the copper 5-6 system, where now the 5 element can actually be both in the 5+ or the 3+ oxidation state. Whereas in a 3 system, only thallium could be aliovalent. All of these systems can exist in the 3+ and the 5+. So we can very quickly look at the absorption spectra theoretically, and eventually, as I'll show you experimentally, for these copper 5 systems. Compare the low valence system with the high valence system. And when we do that, and here's a case of just antimony 3 versus antimony 5, 2 compounds theoretically, what we see is that the lower valent antimony has a quicker onset and a much stronger absorption than the higher valent antimony. And so we actually see, particularly if we look at this system, that so then we actually can look at this system both theoretically, which is what the dotted lines are here, and we've actually looked at these now experimentally, and our folks at Oregon State have been able to show that these systems actually do have stronger absorptions for the lower valent system than for the higher valent system. And if you look at the, if you just integrate the density of states of the conduction band for the P, for both near the valence band and the conduction band, you see very quickly that there's more P in the copper, in the group 5 3+ system here. And if you go look at the S content, you actually see that there's actually a lot more S now in the valence band. So we've actually been able to show both theoretically and experimentally how we might manage and understand absorptivity in inorganic thin films, and how that absorptivity correlates with respect to the densities of states of both the conduction band and the valence band. And so now we're very interested in trying to realize some of those systems experimentally, and so at Oregon State they've been actually able to take layers of antimony sulfides and copper, anneal these systems into some polycrystalline systems, and see some of these absorption differences. And you can see that there's actually a rapid onset of absorption, and that some of these systems might be even superior to some of the copper indium selenide systems. Of course, we have to now worry about doping and some of the others. But this is a good way for us to start to explore the periodic table in a fairly quick way for some of the key properties and functionalities. And in fact, we're using this methodology now. I think one of our key successes has been we've been taking this methodology and transferring it to our more applied programs. So in our applied programs at NREL, we've been very interested in understanding how we might rapidly develop some of these known absorbers, whether they're the copper antimony sulfide systems or the copper tin sulfide systems. And we've been able to do this very similar type of method where we've been actually looked at 7 different copper tin sulfur systems and down selected by looking both at the absorptivity and the densities of states, some of the other issues with too many holes in some of these systems, Fermi level pinning in some of these other systems, and we've been able to come up with this material as probably the prime system in this copper tin sulfide family. And we've been actually looking at how to grow this now and eventually how to put this in a device. But we think that this is a fairly promising PV absorber that theory has helped us identify, and we're going to continue to study it. I want to show you one more example where we actually look at P-type transparent conducting oxides. So there's a lot of cases where you would like to have a P-type TCO, and we'd like to actually think about how to design that. So I'll talk a little bit about some of our design principles for that. I'll talk about how we do a search, and we've identified the spinel systems, A2BO4, a set of metal oxides, as a really good class to start with. And I'll talk about some very detailed work on a system we identified there with the right type of doping mechanisms, looking at a copper-zinc system, and how we've actually been able to increase conductivity by understanding the conduction possibilities there. And so if we think about making a p-type transparent conducting oxide, we need to have high hole concentrations, so we need to do a lot of work on defect calculations, and that's been our starting point. And eventually we need to think about hole mobility and transparency. And so with respect to thinking about high hole concentrations, we've taken a look at these spinel systems. We've looked at about 40 of them in the ICSD database. I'll talk about those in a moment. These spinel systems are pretty interesting. They have a 3+ cation that sits on octahedral sites, and they have a 2+ cation that sits on tetrahedral sites. And actually you get anti-site defects when those switch. And that turns out to be one of the fundamental doping mechanisms in these systems. And in fact, there are spinel systems that actually are inverse spinels, where the 3-type cation goes both to the octahedral site and to the tetrahedral site, and the 2+ cation actually also goes to the octahedral site. And you can actually imagine that might allow you some additional doping and conduction mechanisms. So we've looked at these systems. Unlike other oxides, spinels turn out to have very low concentrations of oxygen vacancies, and they don't really have any interstitials because they're able to move back and forth. And so the primary doping mechanism in these systems are this anti-site defects as opposed to conventional, say, binary. So we did a lot of work looking at calculating dopants and defects, and that's critical to our whole design here. We have the supercell approach that we've used to calculate the energies of defects. We find that the main defects are these, that if you put the 3+ cation on the tetrahedral site, you create a donor. And if you push the 2+ cation on the octahedral site, that's an acceptor. That's actually a hole producer. And in fact, we've then looked at the 4 types of doping mechanisms, which is what is the level of this donor and this acceptor. And it turns out there's one class here that is extremely important. And that is where the donor is actually electrically inactive. It's buried in the valence band. And the acceptor, or the hole producer, is actually out here. And that allows you to get to a p-type system. The other system that allows you to get to an n-type system is if you could actually bury the donor, the acceptor into the conduction band and have the donor there. And so this is a system that we've looked at. We've actually looked across these systems. Because this is electrically inactive, we don't have any intrinsic hole killers here. So if we can get more 2+ cations onto octahedral sites in these spinel systems, we should be able to get pretty significant doping of these materials. And so we've actually looked at a set of spinels, and it turns out of the 40 spinels we looked at theoretically, 12 of these are this naturally p-type, where the donor level is buried in the valence band and the hole producing acceptor layer is actually in the gap. And when we look at these systems, we actually take a look and say this is a pretty, from a toxicity and low cost, copper and zinc seems like a really good prototype to get started with. So we've actually started to do some very detailed studies on this. One of the first things that we did was to say if we want to make more of these acceptor systems, we need to go zinc rich. So if you look at the theory, if you go zinc rich in this, you start to throw zinc on the octahedral sites, and you would expect the conductivity to increase. Now, as we do that, we've actually been able to see the conductivity increase from below 0.01, and we actually end up, if we look at this under equilibrium conditions, it's very hard to make this, and we get a phase separation to a zinc oxide material. But if we look at this on sputtered films, particularly with low substrate temperatures, you see we can get this non-equilibrium growth where we've made these zinc rich and get much higher conductivity than we do in the higher temperature systems. And as we actually anneal these films, we see the conductivity decrease, and we think the anti-site defects are reversed. And one of the things we then asked is if we could put this, this is kind of a self-doping, having the zinc go to the tetrahedral site. But what if we took other dopants, and here's one where we actually, we looked at 17 different dopants, 3 very good dopants that theoretically should increase this, whole concentration, are lithium, nickel, and magnesium. And here's actually our experimental calculation for what magnesium would do at small levels, going where magnesium would go to the tetrahedral site, to the octahedral site. And we actually see experimentally that magnesium doping gives us a factor of about 5, up to about 5%. We got very interested in looking at the nickel system next. And nickel, of course, also makes inverse spinels. And so we actually then looked at, and this is a combinatorial setup where we sputter zinc oxide, cobalt oxide, and nickel oxide. We can make these gradients. Basically, here is the copper zinc oxide spinel that's normal. On the far right would be all nickel, and that's actually the inverse spinel, where nickel is on the octahedral site and cobalt is on both the octahedral and tetrahedral site. We can do conductivity measurements here, and we can do absorption measurements here. And we can actually find regions where we actually have nickel doping that increases the conductivity, and we actually see higher transparency than we do in either the normal or the inverse system. So we're actually able to now theoretically and experimentally explore this system, understand the doping in these spinels, and allow us to start the design. Now, one of the issues we have here is this system's still not transparent enough. The band gap's about 1.8 volts. So that's not a very good window for visible photons. But in fact, it turns out that this system can be a very good whole transport layer. And so actually with the EFRC out of Arizona State, which has been looking at interfaces for organic photovoltaic devices, we had a nice collaborative publication where we actually showed we could use this zinc copper oxide system as a whole transport layer. This is actually the profile of it. And in fact, the performance is pretty comparable to P-dot PSS without any real optimization. So even if we can't get all of the functionality, say transport and whole concentrations, we can get some of that functionality for other applications like whole transport layers. So those are 2 examples where we look at at materials that are known, and we look theoretically for screening them for functionality, and we work experimentally. The next case is actually, what about materials that aren't yet known? And there's plenty of materials that we don't know about yet. We just don't know about them. Properties have been previously extracted. So many people have gone through and said, if I could make X, I'd want that. One of the examples is simple ABX. And if you look in the literature, plenty of people have talked about properties for these Half-Heusler compounds. But very few people have talked about whether they could actually exist. Are they stable relative to other components? And some of these materials might be very good for alloying. So Vladis Ivanovic and Xuan Zhang and others in our EFRC set about to try to understand how we would look for missing materials in certain classes and what we would need to do. And there were really 2 general ways to go about this. In a perfect world, you would want to do something like a global space group optimization, genetic algorithms, and just explore the entire structural space. You can imagine that's very difficult and takes a long time. And in fact, one of the tricks, I think, to materials by design is how to do the right kinds of theory without trying to do everything all the time, everywhere. And so our alternative has been to actually start with composition, with stoichiometries, and to explore the structure types for those known stoichiometries, and then actually change the elements beyond what's known. And so we actually now use theory to sort out the ground state structure, looking at 39 different structures. And one of our cases is this A2BX4, these spinels and others that we talked about. And so what you want to do is there's 406 possible A2BX4s out there known, 39 structure types, and several magnetic configurations. And so now you need to set up actually about 80,000 calculations to explore that space. And so we have the platforms to do high-throughput theory, and we actually did that. Set these up to run. We have some automatic detection of errors, quite a bit of data management as well, and extract the properties out. And so I just want to talk about how we would approach that. Think about a compound that that you don't know if it exists. What you have to ask is that compound, say A2BX4, how is its stability relative to all of its constituents? Whether it's all of the elements, whether it's other phases, or other materials. And so you need to actually look at what are all the possible phases, what is the structure and the energy of this, calculate the energy of those materials, and then also get rid of the elemental reference energies, and you can determine which of these should be stable relative to that. And so that would be great if DFT was good at giving you good heats of formation, but in fact it's not. For alloys, for metals are compared to elemental metals, DFT is really good for heats of formation. But you see, as soon as you go to even binary oxides and nitrides, the error bars in DFT are actually horrendous. And in fact, the error bars are a lot greater than what you think some of the deltas might be per atom between known materials. So we needed to come up with a way to make DFT work better. And so we actually came up with a very simple way, which is this fitted elemental phase reference energies. And that is that we looked at fitted known values, calculated values for 252 binary compounds where the heats of formation are known. And we went through that, and we could actually provide an elemental correction for each transition metal and each other element in the periodic table based on that fit. And we could actually then use that to calculate other compounds that are known. And so what we did is we calculated those corrections for each of these elements for binary systems. And then we actually looked at, using those, what do you calculate energetically for ternaries. And in fact, if you look at known ternaries, we can actually get to within about 0.05 EV per atom for all of these ternaries using the correction factors for each element from our binaries. So this is now a very simple way for us to use DFT to look at heats of formation of a whole lot of compounds. And that turns out to be really important, and that's how we do this work. The other piece, of course, is to think about the chemical potential for each of these elements and to ask, how would I work in what process space? Because some material might be stable under high oxygen concentration, but not under low oxygen concentration. And so here's an example of how this works. Here's a compound. We predict, if you look at its relative to just the elemental competing phases, it has a negative heat of formation, so it's stable over all these process conditions. But if you start to think about other materials and you bring in MNO as a potential decomposition, you see now it's only stable in a much narrower window than it would be. And if you actually bring in other materials, other manganese oxides, silica, you now find that it actually is only stable within this window. And you can now take these chemical potentials and say, it turns out, if I look in the literature on where this material is actually made, it actually fits right into the chemical potential of oxygen that's right in that window. So you can make it here, you couldn't make it here, you couldn't make it here. So that becomes very important for how to actually process a material that you predict to be stable under some conditions, but not others. And in fact, it's great if you can think in chemical potential space. I don't. I think in things like temperature and partial pressure of oxygen. So you can convert that diagram I just showed you into a log of PO2 versus temperature. And so here is where MnSiO4 is stable. Here's where it's not stable with respect to the elements. Here's where it's not stable with respect to other oxides. So this window is that little box we defined. And in fact, that is where that experimental point fits in that processing window. So that becomes a very important tool for theory to help understand where to make things. And so now let's try to see what we can find. So now let's go back to our old friend A2BX4. Let's take a look at A and B and X. Let's use only one transition metal at a time. Let's respect their normal valencies and oxidation states. And let's take a run through. And so of the 656 possible combinations here, 406 are not reported, only 250 are. So what about those 406? Are they not stable, or are they possibly stable? So we actually take a look. Here's A, here's B. If you look at the check marks, these are the ones that are reported. I mean, the O's are the ones that are reported. And then all the other ones are the ones that we filled in. And so the ones with circles are actually reported, as I said. The ones with checks are ones we predict to be stable. And the ones with X's are ones that we do not predict to be stable with respect to dissociation to their other elements. So again, 80,000 calculations. We can find that of the 63 oxides that are not there, 46 of them are not stable, but 17 of them, including these, are stable. And if we go back and change X and look at the sulfides, out of the 92 not reported, 34 of those are stable. One is too close, undetermined, not undermined. One is too close to tell, and 57 of those are not stable. But there are new materials that should exist and could potentially be synthesized. And so out of the A2BX4 materials, 684 variations, 429 are unreported. We predict 100 of these to be stable. 11 of them are hard to tell, and 318 of these are not stable. So spending a lot of time calculating properties on these unstable ones doesn't make a lot of sense. And so calculating them on these makes sense. So in addition to these A2BX4s, which we've studied in some other areas, we started to look at ABX materials, both with 18 electrons and with 8. And a couple years, last year we published a paper that said if we look at ABX, the same A's and B's, out of 714 variations, 488 are unreported, 235 are predicted to be stable, 18 are hard to tell, and 235 are predicted not to be stable. And so these are these half-Heusler compounds that people have spent a lot of time trying to understand what is their technological relevance. And so now we want to talk about how we go about making these materials that we can predict to be stable. And so one nice quick way is to actually very quickly try to make these systems, and we actually use theory to actually go through what are the stable ones that are not reported. And this is actually now for the 18 electron systems. And of those 58 stable ones that are not reported, one of these has this crystal structure, 15 of these have this, 2 of these have this. We can actually predict the crystal structure for every single one of these. So now we can do synthesis and look at powder XRDs to see whether we can make these materials. So we can very quickly look at the symmetry of these systems, simulate the diffraction pattern, and in our rapid synthesis experimental method, see if we can see these XRD patterns. And so here's an example of this, recently submitted to Nature Materials, our colleagues at Northwestern and CU. Several of these compounds were predicted to be stable. One of these examples is this system with this crystal structure, predict this crystal structure, and actually calculate what that XRD ought to look like. Try to make this system either in bulk or on a thin film, and you can actually confirm its presence. And so very quickly we can see that some of these are stable. So we want to now go the next step and say we don't just want to make materials that haven't been made before. There ought to be a real reason for it, and of course functionality is our reason. So now let's take another look at this ABX system, and we want to actually start doing some calculations on functionality. So here's one, tantalum, cobalt, tin. 3 metals combine in an ABX and actually make a semiconductor. We calculate an indirect gap at 1.3 volts for this material, an absorption onset at 1.6, and high absorption above 1.8 eV. And in fact, if we look at the calculated densities of states, we can calculate those absorptions. And so now what we want to do is actually see if we can grow this material. So we actually, again, look at this. It's missing from the ICSD database. Turns out if we look at this chemical potential, there's a large stability window for it. And we have looked at all of the different competing phases, although I'll show you another one that comes up. So now we set up a sputtering system. We predict the structure, we predict the X-ray, and we actually use our combinatorial thin film synthesis, map along tin, cobalt, and tantalum, and you can actually see where we can actually make this compound and see its XRD, other places where we can't make it, and other materials that are actually documented in the ICSD database. So this is the region where we can actually make this material. It turns out that we actually can't get a good band gap measurement of that, which was very frustrating. But we've actually been able to demonstrate a new semiconductor that we actually predicted its structure, predicted its properties, and have been able to make it. And so I think this whole framework allows us to think about high throughput theory and experiment, think about functionality, start with stability, identify these things in multi-phase systems, determine their structure, and understand their functionality. And so as we think about our Inverse Design Center, we've been able to tightly couple experiment and theory. We've developed a number of tools and processes that allow us to do this. I've showed you three examples. There's selection criteria for PV absorbers. We talked a lot about these spinels and these oxides for P-type TCOs, and now how we're actually searching for missing materials with functionality we can identify theoretically. So certainly this approach ought to be fairly broadly applicable. We're thinking about other functionalities. We've been looking a lot at water splitting and band alignment in semiconductor materials. And also I introduced the concept a little bit, but we're now thinking much more that it's going to be very important to address metastability and not just think about materials that are on the convex hull, but those systems that we could get under non-equilibrium growth. And in addition, how we might think about the process conditions and guide experimentalists for the synthesizability. So with that, I just want to end. I want to tell you one other thing real quick, and that is that we think a lot about technologies for the U.S. And certainly how technologies get adopted in the U.S., there's a lot of regulatory and policy constraints that are very distinct from a lot of the technical considerations. And as scientists and engineers, we think a lot about the technical considerations. But I want to also get you to think, and I'm sure you already have, that there's a whole other world out there that may have very different problems, may need very different technologies and very different time frames. And so I just want to tell you just for a moment about a consortium that we actually put together 2 years ago, the Solar Energy Research Institute for India and the US, or SERIIUS. This is 31 institutions that is led by NREL and the Indian Institute of Science out of Bangalore. It has a number of companies in it. This was actually a DOE program that started. We're really trying to create innovation without borders here to develop and ready technology, solar energy, both for the NREL mission and for the DOE Sunshot mission. The DOE Sunshot mission is this $1 a watt to get to grid parity for solar energy. The NREL mission is about putting 22 gigawatts of solar out into India by 2022. And these are solar resource maps that have been actually done by NREL in the US. And compared to places like Germany that actually have a lot of solar, you see we have a lot better solar resource, and so does India. And so we have a three-thrust research program looking at sustainable photovoltaics with a focus on earth-abundant PV, looking at multi-scale CSP, really the concept of trying to look at concentrated solar power at much smaller scales than we think about it in the US, and trying to not have what we call a scale-down penalty. And then the last one is to actually understand how that solar energy might be integrated and what some of the key research needs are. Of the projects we have, half the projects are funded by DOE, and half the projects are actually cost-shared by both US and Indian companies. And so we set up a nice two-tiered structure where we have pre-competitive consortium projects with government funding and protected core projects that are firewalled with the companies and the few PIs that are working on that project on projects that are much more specific to companies. And one area that we've been working on extensively is to actually think about low-cost atmospheric processing. And so a lot of work on developing inks on roll-to-roll type processing and what that processing might be. And one of the things that we've actually been able to demonstrate at NREL recently, outside of SERIIUS, but I think it's really important, is this is actually flexible willow glass from Corning. And we've actually been able to deposit cad telluride. Teresa Barnes and her colleagues at NREL have worked with Corning and have made a flexible cad-tel device. And it actually has a pretty good efficiency and fill factor. I think it's about 13%. So we're really interested in what these and others might do, on some of these flexible substrates. And I just want to leave you with the thought that there's actually a strong synergy between some of the basic research needs in India and the US, understanding some of the critical barriers for photovoltaics, as well as other solar energy conversion technologies can be very important. But there's also some very specific Indian considerations. 400 million people in India are off the grid today and don't have electricity. And so how they might use solar energy and storage might be very different than how you might use it in Santa Barbara. And reliability turns out to be a very different beast in India. The dust can be different, the combination of pollution and dust, the environmental factors. So reliability may be very important. And as we think about smaller systems, some of our economy of scale people are taught about as chemical engineers for thermal systems. When you scale them up, we actually invert that and you have a penalty for scaling them down. So how do you think about processes that can actually run at much smaller scale? And with that, I just want to remind you that we not only need to do the solar energy conversion, but eventually we're going to have to store this stuff, whether it's as heat, as electrical, or as fuels. And so that's going to continue to be very important as we think about broad scale, high penetration, renewable energy. And I just want to acknowledge for the bulk of this talk all of the hardworking people from our Center for Inverse Design. I want to thank Dave and John again for the kind invitation. I really enjoyed talking with a number of faculty today. Was very impressed with your facilities. And I want to thank you for coming and your kind attention. Thank you.
Questions? With this predicting stability, what kind of percentage of false positives and false negatives do you have?
That's a great question. So the answer is we don't know yet. And so, you know, there's always a debate. When a synthetic chemist isn't making it, the theorist tells them they're not very good, and the synthetic chemist says you better go back and check your calculations again. What we have found sometimes, and turns out to be really interesting, is of course that dissociation into other phases is only as good as all the phases you identify. And in fact, there's been a couple synthetic attempts where we've actually identified new phases. And then if the theorist incorporates that phase into the calculation, they say, yes, that is actually more stable than this. So some of the false positives or false negatives turn out to be, we haven't considered all of the possible other compounds that this could dissociate into. So that's where some of the combinatorial methods can be very helpful, because you can pop out some of these other phases and get those into it. Of course, the fact that there's a well somewhere doesn't mean you can get to that well either, right? As a chemist, I mean, we think about mechanisms for synthesis, not just, my sputtering guys like to just say if A and B are there, right, and I can get it together, it ought to work. And it's like, well, that's a possibility. And you're often very fortunate, but not always. Sorry, John.
Along that line of stability, the only time I've used somewhere you're talking about like anti-site defects or stoichiometry to make p-n junctions, Merck-Cadtel.
Aha, yes.
Really, it's not very stable, right? You sort of sneeze on it and junction at the surface. So it always seemed to me it's better to be put in other materials rather than using vacancies or something to give you stoichiometric changes to get your junction.
That's an interesting point. I think in some of the spinels, some of these systems can be pretty stable and they don't anneal out as well. I don't know in the 2,6 systems, you know, what the stability of those are. Not just, I mean, not thermodynamically stability, but what the kinetic stability of some of those systems are. I think kinetic stability is going to be really important for metastable systems in general, not just identifying where it is or how it can decompose, but how deep of a well it sits in. I don't know, a Merck-Cadtel, it might sit in a very shallow well. One of our hypotheses for things like these oxides is I think the dislocations become much harder to do. And so we've actually been thinking about how to identify what kinds of crystal structure changes can happen to allow that site exchange to happen, and where that might be kinetically a big issue versus not. And so I think the depth of the stability is going to be important. Predicting it a priori is going to be pretty difficult, but that's an area we're thinking of challenging. I don't know enough about Merck-Cadtel, but that's a good story. So.
Well, have you thought about applying this to organic materials for applications to organic solar?
Yeah, so actually we do that, and we do that in our, we do that more in our applied energy, in our ERE programs, and we are actually doing that, I think, in some of our collaborative work with others. So we have a set of organic theorists that that are probably much more Gaussian 80 types than, or what they're called today. Walter, I don't keep track of Indo, Sindo, and what the organic chemists are using now, but quantum chemistry, and rather than some of the solid state theory. And they've been doing pretty well, and you know, there's a couple of things they're trying to do there. Understand some of the band alignments, but also trying to understand if you make mixtures, can you actually cover a much broader absorption set? So I think that's a very important area. We've not done it in this system. It's a little geopolitical. There's a lot of organic photovoltaic EFRCs out there, and we didn't want to become another one of them from a funding perspective. But and there's some very good ones out there, and I know one here that does very well. So sorry, John. So we just started an LDRD on thermoelectrics. So one of the ideas here has been that with this EFRC, we've been able to create a pretty good foundation. And so now we're looking for some outlets. So a year ago, we started the copper tin sulfide work on ERE. And of course, ERE wants a little shorter, kind of milestone-driven research. So you have the tools set, and you apply the tools. We just started an LDRD with Eric Tober and some of our folks at NREL trying to understand thermoelectrics and how we might do some of that screening. But we could use a lot more help, as we talked earlier today. And I think that's an area that makes a lot of sense. And then, and we actually have a combi, a rapid CBOC coefficient system that Andrei Zakatayev has actually set up at NREL now. So we can do some important work there, I think. I bet it does, yes. I don't speak in phonons too well, but I think that's an important piece, and I'm not sure how well, I'm not sure what they've thought through on that, but that's going to be really important. I think they're starting with the conductivity piece, but the phonons are going to be the killer, are critical, of course. And in fact, working the denominator is probably better than working the numerator in some of those ZT systems. I think this, as we talked a little bit, I think these lower temperature, kind of lower grade systems might be amenable, and how do we get out of the bismuth and other systems where people have seen the successes so far. Some of my friends like Gerd Cedar at MIT and the Material Project at Berkeley are doing a lot of work in battery materials, so we've steered clear of that, but I think they're finding a lot of help there looking for screening. So there's a whole lot of, and you know, Jens Norskopf is doing a lot of work on catalysis, where you have to kind of bring mechanism in, not just band structure and optoelectronic properties. So I think it's pretty impressive. Actually, if you want to have fun, Google materials by design and find out how many materials by design centers there are. So we actually think this metastability question and synthesizability question can be an important distinguisher for us in the future as we move forward, and we're focusing more on that, with other functionalities still involved.
There's another question in the back there.
Yeah, that's a great question. The answer is I'm sure. I think we still, in those systems, need to know what questions we need to ask before we need, and what questions need answered. I've been beating on my troops a bit and saying, you know, what is our position on perovskites and what do we think about these? You know, it's a drift cell versus this kind of system, but I think it's a really good question. But I do know you want to be careful when you get theorists in a room to make sure you frame the question well. Because they'll give you the answer, but you've got to make sure that the question's framed really well. I think in that system, we're still trying to understand the questions.
Okay, well, let's thank our speaker.
Thanks.
Great, thank you.
Thanks. I hope that was okay.
Oh, it's actually really good. I've never actually heard Dave talk about the Center for Inverse
Aha,
Design,
okay,
so
good.
I was thinking I wish we had asked him long ago.
Well, the stories are pretty good. There's some more complex ones we're looking at, but of course they don't tell the same easy story that these do. But yeah.
One other question
Yeah.
on your India stuff. So
Yes.
we work a bunch. We've got a nonprofit that does solar-powered energy